Okay, so the third point is to prove that, the third item is to prove that conjugation preserves order. So we want to prove that conjugate elements have the same order. And the fourth item is to prove that U17 is generated by 3 and also generated by 5. Hence, U17 in particular is cyclic. Probably generated by other things too, but if we get to it, I mean, we'll only show that it's generated by 3 and 5. Okay, so number 1. So prove that conjugating R alpha by a reflection gives R negative alpha. And this is in O2. So I guess there's a bit of ambiguity, because if I just write R alpha, it could mean an element of the dihedral group. But I mean, only certain rotations are in the dihedral group. O2 contains all rotations and all reflections. Okay, so there's going to be two ways of I'm going to demonstrate two ways of doing this. The first way will be algebraic, and it's more what you would write on a homework or an exam. And the second way will be more intuitive, and it probably wouldn't suffice as an answer on a homework or test, but it is helpful to have some intuitive understanding when such an understanding is available. So we'll first do the algebraic way. So this is what you would write on a test or a homework. I mean, maybe there's other things you could write on test or homework, but this is an example of what you would write. So consider the reflection FL, and I'll draw L. Whoops, alpha is already an angle, so I'll make this theta, where L makes an angle of theta, or you could do pi plus theta with the positive x-axis. Then, if you conjugate alpha by FL, I guess I should say the conjugate of R alpha by FL. Okay, conjugation of R alpha by FL results in this element. So we have to show that FL inverse R alpha FL equals R negative alpha. That's what we need to show. And we'll prove this by showing the matrices for these transformations are equal. So the matrix for FL inverse R alpha FL is cos 2 theta, sine 2 theta, negative cos 2 theta, sine 2 theta, and then alpha will be cos alpha I mean, R alpha will have this matrix, negative sine alpha, cos alpha, and then again a matrix for FL. And I want to make a note here. Note that FL inverse equals FL. So FL inverse and FL have the same matrix. So remember that reflecting twice gets you back to where you started. So if you reflect over a line and then reflect again, you're back to where you started. So the inverse of reflecting is just the same reflection. So FL inverse really just means FL. But the reason I write FL inverse, so maybe that's a bit confusing. So it's like, why didn't I just write FL? Is because in general, conjugation is something inverse times something times that original thing. So it's like G inverse HG. So I just wanted to match the form of conjugation. But in this case, it happens that G inverse equals G. So this is the matrix. And then what does this equal? So this equals, I'll just multiply it out step by step. So I'll keep the first factor and then multiply the two factors on the right. So I'll get cos 2 theta cos alpha minus sine 2 theta sine alpha. And then here will be sine 2 theta cos alpha plus cos 2 theta cos alpha. Here will be cos 2 theta sine alpha plus sine 2 theta cos alpha. And the last one is this. So then I use the trig addition formulas. So using the trig addition formulas, well, this will be cos 2 theta plus alpha. This will be sine 2 theta plus alpha. This will also be sine 2 theta plus alpha. And this will be negative cos 2 theta plus alpha. And then there's another step. So maybe I'll do that on the next page. So then this equals, but I'll have to keep looking because I can't remember these matrices. So cos 2 theta plus alpha, cos 2 theta plus sine 2 theta plus alpha, sine 2 theta, and then sine 2 theta plus alpha, cos 2 theta minus cos 2 theta plus alpha, sine 2 theta, right? And then the same thing again. So sine, wait, is it the same thing? No, it's the negative. So this one will be cos 2 theta plus alpha, sine 2 theta minus sine 2 theta plus alpha, cos 2 theta. And the last one is cos 2 theta plus alpha, cos 2 theta plus sine 2 theta plus alpha, sine 2 theta. Right? Yeah. Okay, so then again, one last application of trig addition formulas. So the top is equal to cos 2 theta plus alpha minus 2 theta. The top right is equal to Sine 2 theta plus alpha minus 2 theta, right? Yeah, I think so. And the bottom is just the negative. So this is negative sine 2 theta plus alpha minus 2 theta. And the bottom right is the same as the top left. So it's just cos 2 theta plus alpha minus 2 theta again. So then this is actually just equal to cos alpha sine alpha negative sine alpha cos alpha. Uh-oh, it doesn't match the form for a reflection, a rotation, or a reflection matrix. So right now it doesn't seem to match the form for rotation or reflection matrix, but actually if you just use negative alpha instead, it does. So it does match the form, but I just wrote it in a bad way. So if I write it like this now instead, then this is the matrix for R negative alpha. So never mind, it does. Yeah, so that's all there is to it. I mean, it took me a bit of time, but it was really quite straightforward. All we did was just trig addition formulas that we just multiplied some matrices and applied some trig addition formulas. Are there any questions? Okay, so that's one way. And then I promised there'd be a more intuitive way of doing this question. And intuitive, so this way is intuitive, so it's not what you would write on a homework. Not what you would write on a homework or a test. So first of all, I mean, why am I telling you it then? I think there are two reasons. One is if you're just interested in the material, it's good to maybe, it could be, it could be useful. I mean, if you're interested, it could be good for you to see different ways of understanding the same argument. But also, I think more practically, if you are interested just in your performance in this course, it is often useful to have like intuitive checks when you're doing long calculations. So like if I messed up somewhere in my calculation, and let's say the question didn't tell me to prove that it's R negative alpha. Let's say it just asked me what this transformation is. Well, if I have a more intuitive way of getting the answer, even if I don't write it down on the test, I can keep that way in mind, get the answer quickly in an easier way. And then when I'm doing my calculation, I'll know if I messed up anywhere, if I don't get the right answer. And this is, if this question didn't have R negative alpha. So it already told you it's R negative alpha, but imagine it didn't. And, like this is a common thing. Like, for example, if you have an integral and the function's symmetric, before you do any calculation, so even if you're asked to prove that it's zero using a calculation or something, like using the antiderivative, just because it's symmetric, the answer will be zero. So sometimes, yeah, it is useful to have alternate ways of getting the answer to something. So this is the intuitive way. And it basically comes down to a motto, which is that conjugating an element is like looking at the element from a different perspective. So this is intended to be kind of just a vague guiding statement. And so what does that mean here? So here again, in this case, conjugating R alpha by FL is like looking at R alpha in the reflected plane, i.e. the plane after FL has been applied. So remember FL is, so what does FL do? Let me draw it. So there's X and Y. And why am I drawing these arrows? I'm drawing these arrows because any linear map is determined by where it sends basis vectors. So I'm drawing the two basis vectors of the plane, and any linear map is determined by how it acts on these vectors. So in particular for FL, what does it do to these vectors? So this is my line L. So if I apply FL, I get this. So this is what I mean by the reflected plane. So it's the plane. It looks the same, I mean, visually, except that I'm keeping track of where the basis vectors have gone. So if, even though L is in the same location and the axes are in the same location, I'm looking at these two basis vectors, which determine a linear map, right? Like any linear map is determined by where it sends basis vectors. That's a fact that hopefully you learned in linear algebra. If you didn't, then don't worry, because I mean, I already gave you a way of solving this question, but try to give you more intuition. But so this is like the plane, but I've kept track of how FL acted on those basis vectors. And now I can ask, what does R alpha look like in this reflected plane? So I'm kind of asking, what does R alpha look like from the perspective of FL? So let's see. This is the plane after FL has been applied to it. So this is where the Y vector goes. This is where the X vector is. And now let's say I apply R alpha. So what will happen? Purple line. And then my basis vectors will rotate. So let me draw where they originally were using dashed lines. X, and then I'll draw where they end up. So, and I'll pick some random value for alpha. So let's say this much is alpha. So this is where Y will go. Then X will go here. And let's say this is my alpha. So this is alpha, and this is also alpha. So now the point is, and I'll write this in words, even though we've rotated by alpha clockwise and counterclockwise, if we look relative to the basis vectors, we've actually rotated counterclockwise. Well, I mean alpha. Clockwise. So that's the key point here. So if I just look at that picture there, I have my y, I have my x, and sure, the actual transformation I did was R alpha. But if you actually look relative to the basis vectors, what you've really done is R negative alpha, because the basis vectors are rearranged, right? X is in the wrong location. But if you put X in the right location, so maybe I'll write that too. Note X and Y are flipped. So if you actually put X and Y in the right locations, and see what's happening here. So we're rotating by alpha, but look, like X is going opposite to Y. So it's really a rotation clockwise. If you actually look at where they're moving relative to their original positions, this is what's actually happening to them if they're placed in the right places. So this actually, this equals this. Which is R negative alpha. So this is intuitive. So by its nature, it's a bit confusing. It's not as precise as just multiplying matrices. But like I said, for multiple reasons, there could be value in having an intuitive understanding. And this is it. The idea is when I say, what does R alpha become when I conjugate it by FL? What I'm saying is, if you apply FL and look at this reflected plane, and then you apply R alpha, what is the actual change that occurs from the perspective of the basis vectors? So not, even though what I'm doing to the plane, like overall, is just R alpha. Like right now, yes, I've rotated by alpha counterclockwise, but since the initial reflection switched the basis vectors around, like look here, right? X and Y are not in the right order. They're supposed to be like this. Because of that, if you actually look relative from the perspective of the basis vectors, what our alpha is doing, it's really rotating them alpha clockwise. So in other words, from the perspective of FL, R alpha is R negative alpha. So from the perspective of a reflected plane, rotating by alpha counterclockwise is actually a clockwise rotation of alpha. And so that's like, so the point is you can get the answer much faster than by doing a calculation. And this is like, right, yeah. So you can get the answer much faster than by just doing the calculation by multiplying the matrices. And like I said, there's advantages because, while I was doing this calculation, I knew what the answer was going to be. So for example, when I got here, I didn't think I made a mistake. I knew that it was just R negative alpha in some different form. And that's a useful analogy to keep in mind for conjugation in general. So always you can think of conjugate elements in any group as being the same element, but from different perspectives. So remember that one of the items on our agenda is to prove that conjugate elements have the same order. And that's why, because they're really the same element, but just under a different perspective. And so therefore their order is the same as well. Are there any questions? Right, so we can move on to item number 2. Compute the orders of the elements of D6. So first I'll do the easy ones. The identity has order 1. Any reflection has order 2 because reflecting twice is the identity. Reflecting twice does nothing, right? If you reflect and then reflect again, you're back to where you started. So any reflection has order 2. So all that's left are the rotations. And I already did the identities, so there's only 5 rotations, and I could just look at them individually and tell you all the orders. I think it might be more useful if I just told you a general way of finding the order of a rotation in Dn. So instead of, what should I write? We'll describe how to find the orders of a general rotation in Dn. So yeah, how do we do this? So consider a rotation of k steps counterclockwise in Dn, i.e. an angle of 2 pi k over n or 360 k over n. So I like saying steps more because I mean Dn is something discrete, right? Like you only need n pieces of data to communicate what's happening in Dn, right? Like I just tell you where each vertex goes. So the whole angle thing feels a little unnecessary. Like, does it really matter that it's 360k over n degrees? Because in reality, what's happening is, if you have 1, 2, 3 to n, then 1 is going to position k. Position k plus 1, and then it's 2, 3 up to n. So that's all that's really happening. Okay, so what is the order of such an element? By definition, it's the minimal number of times such a rotation it's the minimal number of times the rotation must be repeated for the result to be the identity. So now, how do I find that? I'm going to keep simplifying the statement until it's something tractable. So consider repeating a rotation of k steps m times. So you have a rotation that's k steps. What happens if you repeat it m times? Well, that's the same as rotating by k times m steps counterclockwise. So repeating a rotation just multiplies the number of steps. And remember, steps is like how many positions each vertex is moving, right? Like I'm trying to just give a discrete number to describe a rotation instead of giving like a weird angle. I'm just saying, does it rotate at 1 step, 2 steps, 3 steps, or no, 4 steps, so on up to k. So that's the same as rotating by k times m steps. When is a rotation by k times m steps the identity So if you rotate by some number of steps, when will that rotation just be this, send every vertex back to where it started? It's when the number of steps is divisible by n, because there's n positions in total. So if you rotate by n steps, you get back to where you started. If you rotate by 2n steps, you get back to where you started, and so on. So it's precisely when k times m is a multiple of n. And so therefore, finding the order amounts to finding the smallest m such that k times m is a multiple of n. So now the problem is very concrete. So we just have a problem that has to do with numbers. We're given a k, we're given an n. What's the smallest multiple of k, which is a multiple of n? So how do we find such an m? Now this comes down to just your skill with number theory. So here's how to find the smallest m. So the greatest common factor of k and n is by definition GCD kn. So the reason I'm writing this is how much of n we get by default. We want a multiple of k to be divisible by n. So we should first see how much of n do we already have just in k. We have GCD kn. That's exactly the amount of n we have covered because it's the largest common factor of GCD of n and k. So to get the rest of n, we have to multiply by n over GCD kn. So that's the rest of n. So GCD kn is the portion of n contained in k. This is all very vague. I can prove this formally, but I think I'd rather just give you some intuition for why it's correct. And I think on exams and stuff, you can use this formula. I think, I don't know. But I saw in your class notes that your professor already told you in the cyclic group that how to find the order of elements, and this is exactly equivalent to that. So hopefully you're allowed to assume this formula. So I'm just giving you some intuition. So this is the portion of n contained in k, and n over GCD kn is what's required to get a multiple of n. So that's the part we have to actually cover. So therefore, the smallest value of n such that k times m is a multiple of n is n over GCD nk. So that's, and I mean, I reduced finding the order to finding the smallest value of m such that k times m is a multiple of n. So that means the order of rotation by k steps in dn, i.e. 2 pi k over n, or 360k over n, is n over GCD nk. So I have a general formula now that can find the order of any rotation in any dihedral group. And so in particular for D6, it's easy to find all the orders. So in particular for D6, so the rotations are R 2 pi over 6, which is when k equals 1, R 4 pi over 6, which is when k equals 2, R 6 pi over 6, And I'm not simplifying the fractions because it doesn't matter, are 8 pi over 6, which is k equals 4, and r 10 pi over 6, which is k equals 5. So then, so the order of this is 6 over GCD of 6 and 1, which is just 6. This has order 6 over GCD 6 and 2, which is 3. This has order 6 over GCD 6 and 3, which is 2. This has order 6 over GCD 6 and 4, which is 3. And this has order 6 over GCD 6 and 5, which is just 6. And you can easily verify that these orders are correct just by directly looking at these elements, but I wanted to give you a general way of getting the answer. Are there any questions? Okay. Next, prove that conjugate elements have the same order. So first I'll prove it formally. So formal meaning what you would write on a homework or a test. So let's X and G have order n, and let G be an arbitrary element of G, little g being an arbitrary element of big G. So we have to show that, so we want to show that, well, okay, no, I don't want to say that. It suffices to show that G inverse XG has order n. So I'm supposed to show that conjugate elements have the same order. So all I have to do is take some element of some arbitrary group with order n, take some random element, and show if I conjugate by that element, the result has order n. And there are two components to showing this. So we have to show that G inverse XG to the power of n is the identity. That's one part of it. To showing something as order n, you have to show that repeating it n times gives you the identity. But don't forget that order is not just a number that when you repeat the element that many times you get the identity. It's the smallest number with that property. So we have to actually also show that, for any m that's less than n, G inverse XG to the power of m is not the identity. So there's two components. We have to both show that it to the power of n is the identity, the conjugate, and we have to show that any smaller power wouldn't give me the identity. Okay, so first, let's show that it to the power of n is the identity. And here's a very common trick when you have conjugates. So G inverse XG to the power of n is G inverse XG repeated n times. So there are n copies. And then I regroup. And by regroup, I mean I regroup the terms in the product. It has nothing to do with group theory. It's just coincidence that it uses the word group in it. So I regroup and I get G inverse X, G inverse X, G inverse, and so on. X, G inverse, X, G. And this is like I said, this is something that commonly shows up when you're proving anything about conjugation. It's the fact that multiplying two conjugates, the G inverse and G's will all cancel out. So, and then if I cancel, so if I cancel pairs of G inverse, well, I'll just get G inverse X to the N times G. So all these inner pairs of G inverse will cancel out, but then we assumed X has order N. So X to the N is the identity, hence G inverse X to the N times G is G inverse E times G, which is just G inverse times G, which is the identity. Therefore, G inverse X G to the N is the identity. So that just proves one thing. That proves that our conjugate element repeated N times gives the identity. We have to show that no smaller amount of repetitions gives the identity. So for the second part, suppose for a contradiction, so I'm trying to prove that there's no such M, and natural way to prove it is suppose there is such an M and show that you get a contradiction. So suppose for a contradiction that G inverse XG to the M is E, where 1 is less than or equal to M is less than M. So what's wrong with this? Well, the key is that conjugation is reversible. So to reverse conjugating by G, just conjugate by G inverse. That is, well, in particular, we can get X from G inverse XG. We can just conjugate by the inverse element. So X is equal to G inverse XG conjugated by G inverse. So it's G times G inverse XG times G inverse. So in other words, X is a conjugate. So conjugation is a symmetric relation. If something is if A is a conjugate of B, then B is a conjugate of A. So that means, well, X is a conjugate of G inverse XG. That means we could just repeat the argument we just gave. So X to the M is just G inverse XG, G inverse. You repeated M times, and then everything cancels. So after you regroup and cancel, you get G inverse XG to the power of M times G inverse, which is just G inverse, which is just E. Hence, X to the M is equal to E, but 1 is less than M is less than N, which contradicts the order of X being n, right? So the order of x being n means the smallest number of times that repeating x will give the identity is n. But if I assume a conjugate of x has order m, then I can just conjugate back and apply the argument we had before, and I get that x to the m is the identity, which is a contradiction. So therefore, G inverse xg has order n, which completes the proof. Are there any questions? Okay, and your professor requested that we do an example. So I'll try to quickly get through that before time's up. And the example was that if you conjugate r to pi over 3 in D6 by reflection. So let's do that. So let's start with D6. And let's conjugate by, let's say, this reflection. Then we get this. Okay, and now we apply r to pi over 3. So we get 1, 6, 5, 4, 3, 2. And well, if you actually, again, so there's the thing I said before that conjugation corresponds to change in perspective. So we can look after we've applied FL, what does r to pi over 3 do? So if I look at relative to where 1, 2, 3, 4, 5, 6 are, what is r to pi over 3 actually doing? Well, what it's really doing, well, you'll see it in 1 second. So if I apply FL inverse, then I get, and FL inverse is just the same as FL. So I get 2, 1, 6, 3, 4, 5. And this is just the same as r 4 pi over 3. So FL inverse r 2 pi over 3, FL is r 4 pi over 3. And this matches what I said before. So if you look at, oh, and time's up. So thank you for coming. I will just spend like 1 more minute writing something else. I'll just write that the order of r4 pi over 3 is the same as the order of r2 pi over 3. So I will have completed this part. But yeah, thank you for coming and have a good week. I'll stop the recording here.